Chapter 4, as you can see on the screen, is called Applications of Differentiation. So we're going to take all those derivatives that we talked about and we're going to start applying them. How are we going to apply them? Well, we got a whole bunch of stuff coming up. For instance, we'll be doing a deep dive on how to do accurate graphs. And you did this last year in pre-calc, but there were certain things in pre-calc that you couldn't do. Like, for instance, you remember doing the rational graphing where you had the asymptotes and then you had a curve going like this. What you couldn't do is find the height of that curve. Calculus will allow us to do that. We're going to do optimization problems, also known as max-min. You've done 1,000 of those. That's the old a farmer's building a corral to keep his sheep, and he's got 1,000 feet of fencing. How big of a pen can he make? We'll be doing that in this chapter, too. So, we're going to start with some... hold on. Yeah, I think I'd rather be alone.
But you're with us all the time. Yeah.
What's that?
You're with us all the time. It seems like you should be used to it.
Oh, it's a valid argument.
Yeah.
Pretty much that's what I do for a living, right?
Yeah.
Okay. Well, I'm going to stay over there.
Also,
Quiet time is very valued. What's the matter?
You couldn't do your job if you were alone all the time.
It would be a lot easier. The job would be awesome without all of you around.
Okay.
But it would be boring. Okay, so we're going to talk about extrema. And we're going to talk about the difference between absolute and relative extrema. Isn't tight? And we're going to find some critical numbers. Critical numbers become a major chunk of this chapter. You're going to get so sick of those two words, you're going to want to scream, and then you should be able to snap your fingers. Everybody. Can anybody not snap? It's like you have silencers on your fingers. You gotta
Pitch forward one. Pitch forward.
There's a little something there.
Yeah.
I mean, it's not bad, but I've had more time to practice. You're using your middle finger, right? Anyways, let's move on. Okay, so here's a function. That function happens to be x cubed minus 2x. I'm just going to throw out a general question. What can you tell me about that picture? Thea.
It's going in two directions.
It's actually going in an infinite number of directions.
Yeah, that's what
Okay, good. What else? Andy? It has 3 zero values. Excellent. They appear to be at about 0, 1.4 something, and negative 1.4. Do you agree?
Yeah.
Good. Beautiful. Anything else?
It's a
Daniel?
function.
Say again?
It's a function.
How do you know it's a function?
Because
I'm going to need a little bit more than because.
it's a vertical line test.
Yeah, it passes the vertical line test. Very good. What else? Liam?
It has 2 turn points.
It has 2 turning points. I'm not sure I understand what you're saying.
For max and min. But
Oh.
also,
Oh.
yeah.
I don't know. That's what I'm asking you. I mean, I know what you're talking about. I'm pretending I don't know what you're talking about.
I'm not sure.
Because we haven't talked about it yet. Where would those be located?
At 0.7 and negative 0.7.
Okay, good. What else?
An unlimited domain range, or an infinite domain range.
Yes.
Are those 2 points where it turns around where the rate of change is 0? Is that what's significant about that?
Where the what?
The rate of change is 0. Is that what's special about that?
It could be. What else? Maeve?
On the left side, there's an endpoint, and then it's continuous on the right.
So is it still infinite?
What do you mean?
Is the function still infinite? Nathan said it was infinite. It has an infinite domain and it's not infinite.
No, there's an end or the
But there's an arrowhead on the other side.
yeah. It's like one side, it's positive infinity, and then the other side.
So it's not infinite.
It's not.
It's just infinite in the positive direction.
Yeah.
Well, it's still infinite, it's just not all the way on the upper.
Is that infinite?
Wait, hang on. So, okay. So let's say, wait, guys, listen. Let me-
Wait, hold on. You don't get to
Hold on.
take over a
Wait.
conversation. Wait, no, you stop. You don't get to take over a conversation. If you'd like to contribute, you can, but you don't get to dictate what we're talking about. So if you have something you'd like to
Yeah.
share, please do so.
Okay, so, like, if, say, that function, there's an arrow on the left side, right?
It's on the right side, but
Yeah,
that's
but-
okay.
But if there was, then you could make the same argument, I think, because it's, I mean, like, in terms of, like, no, never mind, I'm wrong. Yeah.
Okay.
Okay.
Nathan, let's go back to you. What's the domain of that function?
I don't know the exact point, but
No, ballpark it.
looks like it's about 1.6 and then infinity.
Negative 1.6?
Oh yeah, negative.
Negative 1.6 to infinity. Okay. Maeve, is that infinite?
No.
Okay, I'll come back to you in a second. Nathan, what's the range?
Negative 1.5 infinity.
Okay, thank you. Is that infinite? But it goes on forever.
But it can't go like for infinite, doesn't it have to go both ways?
Oh, interesting. Let's go back to geometry. Remember the good old days? Which is longer, a ray or a line?
Right.
The rest of you, which is longer, a ray or a line?
That's not another question. Yeah, not
Yeah, not a line segment.
That's just me being.
No, not a line, not a segment. Which is longer, a ray or a line?
Ray has one.
Kush, you look very contemplative. A ray or a line?
Alright.
A ray is longer. Why?
I don't know what a ray is.
You don't know what a ray is? Who did that for geometry?
I didn't take geometry here.
Oh, that explains it. You were deprived of an educational opportunity.
Yeah.
I understand. Okay. Posey, which one's longer, a ray or a line?
I also don't know
It's all right. Allie, are you raising your hand or?
Is it a line? Because mine is like 2 arrows and there is one.
Ooh. Okay, so let me ask you a question, Allie. How long's a line?
Infinite.
Beautiful, great answer. How long's a ray? Which one's bigger?
They're the same.
They're the same. Okay. Infinity is infinity. There's no such thing as infinity plus 1, or 2 times infinity, or infinity divided by 2. It's still infinity. Okay? And humans in general don't get comfortable or aren't comfortable talking about infinity. But I understand the logic here. You're saying, Maeve, that if that had an arrow going the other direction, it would be more infinity.
Yeah.
Right. I mean, that's a sloppy way of me to explain it, but the bottom line is infinity is infinity. So that has as many points on it as it would if it had an arrow. Okay. Questions? Anything else about that picture? Liam, let's go back to you. So you pointed out that little humpy thing up there, and then you pointed out that little scoopy thing down there. If I asked you to find those exactly, could you do that?
Yes.
How?
Well, oh yeah, okay, fine. It's when
I gave you the function.
Yeah, when the derivative is 0.
Excellent. Okay, Liam just taught you the entire lesson. Well done. Let's give it up for Liam. Does everybody understand what he's saying, though? Right? By the way, we commonly refer to those as peaks and valleys, or he used the phrases before, max and mins. Okay. Now, Liam, back to you. Let's talk about the max over there, that little humpy looking, that peak over there on the edge. Is that the maximum for the function?
No.
No. Okay, excellent. So this gets, and I'm going to cover a lot of the upcoming slides in this discussion with this picture. That peak that we have over there at about -1, somewhere around there, is what's called a relative max. It's relative max because it's the maximum in a small chunk of the graph. So you're asking yourself, what defines a small chunk of the graph? And I don't have an answer for you. It changes from problem to problem. However, if I was to go back to Liam and I said, Liam, Where is the highest point on the entire graph? You would tell me?
There is none. Or, well,
Infinity, correct, because it keeps going on forever and ever. That's called an absolute max. Absolute, sometimes you'll find some sources will use the term global. So absolute and global maxes are the same thing. It's the ultimate high point of the graph. Okay? I'm close to leaving you alone, but I have two more questions for you. The little valley over there on the right, is that a min?
no, or it's a relative.
It's a relative min. Where is the relative min? Oh, sorry, the absolute min,
Point.
the point. Okay. In that little portion of the graph over here by the valley, this is the lowest point on the graph. But if I look at the whole picture, the dot becomes the lowest point on the graph.
So if the value is lower than the point, would that also be the?
Ooh, excellent question. Let's suppose my graph looks something like this, and the point was up here. Let's try that again. The point was up here, and that wasn't there. Right? That's what you're talking about? What was your question?
Like, would that also be the global?
It would satisfy both conditions. It would be the absolute and the relative minimum, sorry, because it's the lowest point on the entire graph, but also the lowest point in that small region. I wish there was more, but the lesson today is simply that concept. If you want to find a max or a min, you have to figure out where the tangent line is equal to 0. And where is the tangent line equal to 0? Liam?
When the derivative is 0.
When the derivative equals 0. Good. Okay. So there's the fancy schmancy definition of an absolute extrema. You can read that or copy it. It's in your slideshow. You're good to go. It doesn't make a lot. I was some developed an accent. It didn't make a lot of sense. Realistically speaking, it's the biggest value or the lowest value if we're talking about a max or a min. Okay, simply put. And a lot of times in the functions that we're going to deal with, the absolute max or min will be infinity. Okay, so we'll argue later about whether or not infinity counts as a max or a min. We're just baby steps right now. Okay, we answered that question already, right? Different graph, but same thing, right? Take the derivative, set it equal to 0, solve. Okay, do that then, please. Hopefully you all see by now that we're looking for this point. That's pretty easy. And that point. I'm going to talk while you're solving. We're looking for two things with each of those points. We want the x value and we want the y value. The x value is called the max. The y value is called the max value. They do make a distinction between those two things, and they being the College Board, expects you to understand the difference. Okay. One of them is, I'm pretty sure is going to be 0, 0, but the other one is that other guy over there somewhere. Again, the minimum here will be the x value. That looks like it'll be about 1.3 something or another. And then the y value will be the minimum value, which is looks like about 1.2 something or another. Whoops. Okay, any problems? How do I find the y values?
You just plug them in.
Into where?
Into the original.
Into the original function. Very good. Let's suppose you didn't have the picture. Okay? I just gave you a function. All right, see if you can handle this. Let's suppose you didn't have this. And you followed the procedure that Liam outlined for us. You take the derivative, you set it equal to 0, you solve. How would you know if 0 was a max or a min? How would you know if 4/3 is a max or a min? Any ideas? Daniel?
Find the limit coming from the positive and negative side.
Ooh. So how would that help us? I'm not saying it's wrong, I just need a little bit more explanation.
And you could see if they have the same value. Well, if the positive and negative, you see that they're both coming up or down, you would know that that's the lowest point.
How would it differ if I was going to the peak or if I was going to the valley?
Because if you were going to the valley, both numbers would be decreasing. If you're going to the peak, both numbers would be increasing as you approach the limit.
Interesting. It's not a horrible idea, but it would require multiple limits, wouldn't it? Because if I just take the limit at 0, I'll get 0. If I take the limit at 4/3, I'll just get 4/3. So wouldn't I have to get a little bit closer and then a little bit closer to see if that number is decreasing? It would work, but you would quickly realize it's a lot of limits and nobody likes limits anymore. Okay? But we have one option if we can't come up with anything else. Liam?
You could take derivative, you could set the derivative equal to numbers close to see if they're higher or lower. Similar thing, but you need less data.
Okay, so let's focus on the 0, 0, 1 then, right?
Mm-hmm.
If I don't have the picture, I think that 0 might be a max. But I don't have a calculator, I don't know what the graph looks like, I'm not sure. How would I use what you're saying to test that idea?
Yeah, I think if you plug in like, what, 1, then, or like, yeah, if you set it equal to.
Wait, don't use pronouns. Don't say
If you
it.
set the derivative equal to 0.1,
Okay.
then you'll get a lower number. No, you want, it would be the actual function, right?
So you want to plug into the actual function.
So,
Okay. So you're saying if I plug in
yeah.
negative 0.1 and I get an answer
That's lower than.
less than 0,
Yeah, then that means the max.
then it's a max. Interesting. Lauren?
You could plug in a number between 0 and 4/3 into the equation to solve for the derivative and see if the slope is positive.
Ooh. So if we look at that 0, 0 point, what can you tell me about the value of the derivative to the left of 0? Here. Positive.
Right.
And what do we know about the slope being positive? What does that tell you about the function?
Okay.
Have we talked about increasing and decreasing? Oh, maybe we haven't yet. Never mind. We'll get there. Okay. So think about it this way. If we take the derivative of the tangent line, the derivative of the function to get the slope of the tangent line over here, if it's positive, the function's going up. When we hit the critical, I'm using words we haven't talked about yet. If we hit that point that we solve for with the derivative, it's going to be 0. And then if we move to the other side, what's the slope look like on the other side? Negative. So think about walking up a hill. You're walking up a hill, you're going up a hill until you hit the top, and then you're coming down. What about when you go into a valley?
You're going down.
You're going down and then you go up. Okay, good. We're getting there.
That makes sense.
Let me paraphrase this a little bit. This is basically what Liam said in fancy schmancy calculus talk. If you pick values to the left or to the right of that critical number, by the way, that's called a critical number, it's where the derivative equals 0, you can then test by looking at the values of the function. But we're going to find some better ways to do that and some quicker ways to do that. May, getting back to you, if you look at point K, region K, that's where we have a local and an absolute min at the same time. All right. Abby, what can you tell me about the point A? Is it an absolute, a local, both, or neither?
Both.
Both.
Absolute
Min or max? Minimum. Okay. What about B as in badger?
a local max.
Good. C?
Local min.
Okay. D?
Absolute, or both max.
Both maxes, absolute and local.
Yeah.
Okay. And then E?
Local min.
Good. Does that seem fairly easy to everybody? Okay. There is a small problem, though, about C. Think about trying to balance a stick on like a hill or something like that. What's going to be the derivative at C?
Can you calculate that?
That's what I'm asking.
Wait, it would be 0 still.
You sure?
Yes. Only for that, but then after, yeah. It'd be
That point that's described in the picture is what's called a cusp. It creates some weird things. We'll come back to that in a little bit. The other, yes, Lynn?
Can you actually, are there any equations we could actually make that could generate that though?
Oh, sure. Got a gazillion of them.
What?
Some of them I'll share with you.
Okay.
They're coming.
Like not just piecewise.
Yeah.
Yeah. Okay.
Critical numbers. Critical numbers are the points where the derivative is equal to 0. Okay. But there's another twist here, and that is not only do we want where the derivative is equal to 0, we also want where the derivative is undefined. That's an important point that people forget about. The 0 one is simple. I lay a stick up on that graph to the right, it's going to balance up at the top there. It has a slope of 0. The one on the left, as I said, is called the cusp. That derivative is undefined at that point. Well,
Oh, that is a thing?
it is a thing, yeah.
We haven't seen it before, have we?
No.
Okay, good.
Derivative equals 0.
Yeah. So again, critical numbers are where the derivative is equal to 0 or where the derivative is undefined. And we'll see all kinds of examples of where weird things like that happen. It's not just a cusp. This is one example. There are other places where the derivative doesn't exist. We can look at piecewise functions, we can look at corners, cusps, all kinds of fun things. But again, I just want to talk about the basics of critical numbers. That's what I already said. The derivative equals 0 or does not exist gives us a critical number. Have you heard the name Fermat before? Fermat? Famous mathematician?
Yeah.
Fermat's last theorem is one of the greatest unsolved math theorems ever solved recently. That's one of his other theorems. If it's a local max or min, then the derivative has to not exist or equal 0. Wasn't that the same thing we said in definition 2? No, it's the reverse of that. Sometimes reverses aren't always true. If an animal is a golden retriever, then it's a dog. Is that a true statement?
Yeah.
Is the reverse true?
No.
No, it could be a Schnauzer, Shih Tzu, Black Lab. Okay. These two are what's called reversible statements, and they both work. Critical numbers are where the derivative is equal to 0 does not exist. If it's a local max or min, then it must also be where the derivative is equal to 0 or it does not exist. Okay, find the critical numbers for that cubic, please. I'm going to talk while you're working. One of the things that we're going to explore eventually is the relationship between the degree of the polynomial and the number of critical numbers that it has. Oh, cool. So this is a cubic or a third degree equation. We're wondering how many critical numbers there are. And we're also going to wonder if there even is a relationship.
Okay, I did it again.
How many critical numbers did you all get? Two. We started with a cubic. We got two critical numbers. And again, as we do more and more of these, we're going to ask ourselves a question: is there a relationship? If I started with a quartic, for instance, which is a fourth degree, would I get 3 critical numbers? I don't know. We'll see. How'd she do?
Well, should we snap for her instead?
Oh, I mean, yeah, we're all beatniks in the 60s. Okay, so took the derivative, set it equal to 0, solved. If it was a calculator problem, and I will tell you from experience, if it's a calculator, I guarantee you're not going to get a nice, pretty answer like this. Okay? Posey, we know that at 3 on that graph, it's either a max or a min. Which one? Okay. Anybody else? Is 3 a max or a min? Without cheating and looking at a graph.
I guess max.
You would guess max for no particular reason other than you kind of know what a cubic looks like and.
Yeah, I'm guessing.
Okay, but how can we do it without guessing?
That's a good question.
That's why I'm here. That's what I get paid the big bucks for, to ask the good questions.
Like take the derivative and plug in like.
We already took the derivative.
Well, yeah, but then like plug in like -3 and -1 for it, like in the derivative and see what it ends up being. I guess.
Interesting. Nathan?
I know that there's a min because since the slope is positive, it goes like this.
The slope is positive where?
In the first part of the equation, since it's 2x to the third, it's the highest degree number, so it takes the position of the slope number.
So you're using the original function.
Yeah.
Can you do the same thing using the derivative?
Yeah.
Explain.
I don't really know how to explain it.
So let's operate under your assumption that it is a minimum. If I plug in a number to the left of 3, let's say 2, into the derivative, would the derivative be positive or negative?
Positive.
Okay. So the reason I'm doing this is because there's a lot of these types of problems that can be solved by using somewhat logic. Okay, so here's, Nathan has proposed that this is a minimum at x equals 3. Okay? And to be honest, I don't know if he's right or wrong. But if it is a minimum, and I plug a number to the left of 3 into the derivative, let's say over here at x equals 2, what can you tell me about the sign of the derivative?
Wait, like sign?
S-I-G-N, not
Oh.
S-I-N-E. Not the trig stuff.
Okay.
No, S-I-G-N, plus or minus.
Oh. Negative.
It would be negative. Why, Brooke?
Because it's decreasing?
Yeah. If you look at the picture, that line has a negative slope. I don't know how big it is, nor do I care. What if I plug in a number like 4? Positive. Okay, so what if I go back to this derivative and I plug in 2? 2 squared is 4, minus 8 is negative 4, so it's a negative value. Therefore, you were right. What if we plug in 4? 16 minus 12 is positive, times 6 is positive. You were correct. This becomes a minimum. And since we know a lot about cubics, what would happen at negative 2? It would be a max. That's not a very efficient system. We do have a more efficient approach to these, but what I wanted to do is make sure that you understand the theory behind what we're doing here. Looking at the slope of the tangent line, as we approach a max or a min, will help you determine, without looking at the graph, whether it is a max or a min. Okay. Questions on this before I erase it? Okay. Find the critical numbers. Evaluate f at the critical number. Okay, and we'll come back to number 2 is a little shaky. We want to look at the endpoints. Endpoints are simply points away from the critical numbers. And then look at the other values. Now notice this is absolute extrema. It's different than local extrema. This business we went through on the last slide was for relative extrema. This is for absolute. And actually for absolute, they're a lot easier. We don't care about slope of the tangent lines. We just want the y values. Whichever y value is the biggest, it's a max. Whichever y value is the smallest is a min. Best way to organize that, I think, is in a t-chart. So now I've got a quartic and an interval. 99% of the time when you're looking for absolute extrema, you're going to be put into an interval instead of looking at the entire graph. Okay. So first things first, I want to find the critical numbers. Whoops. Come on. There we go. Take the derivative. It turns out to be nice. Oh, I skipped a whole bunch of stuff there. Set it equal to 0 and solve. Huh. That's interesting. This is a quartic with 2 critical numbers. That might screw up our theory later on. Now we have 4 points to worry about. We have the 2 critical numbers, and we have the 2 endpoints. If I go all the way back to the first slide, I'm concerned about the maxes and the mins and the endpoints. That first cubic graph that you saw, remember that endpoint was lower than the min. How do you organize that? I usually do it as a t-chart. Okay, so we're going to put in here 0, no, I lied. What was it? -1, 0, 1. What does it go to? 2? 2. Okay. Could you please plug those into the original function and tell me what the y values are? There are a number of ways to do that efficiently on your calculator. You could put the function into y equals and then look at the table. You could just plug and chug. You could do it by hand. Give me those values when you're ready. Just shout them out. Just anytime you're ready. Give me those values of the function at those 4 points. Sorry? 7 for -1?
Yeah.
Okay. And 0? 0. 1? -1. And 2?
16.
How much?
16.
16. Whoa. 16. All right. I'll ask an obvious question. Where's the absolute min? 1. What's the absolute min value? -1. Where's the absolute max? 2. What's the absolute max value? Anything difficult about that? Hot diggity. Let's move on. Get rid of this. I think we can skip this because we're beating a dead horse here. Okay. Now let's ramp it up a little bit. Yeah. Yeah. Time to quit putzing around with little cute polynomials. Find the critical numbers for f of x, please. Please be sure to use the product rule. Oops, I lied. That's a cubic root. There we go. Remember that whole business last chapter where I said at some point we're going to have to know how to simplify and factor things out? This would be where you go, yeah? Well, this is where it starts. No, I'm going hard. Like it. Keep going. Don't let that derivative get the better of you. School it. The right question. Oh,
Beautiful. Yeah, don't multiply anything out. No. Makes your life way too
I can't see what it is.
I'll trust you on that.
Oh, great question. Don't multiply things out. Since this is our first time simplifying, I'll handhold you a little bit. But if you multiply things out, it makes your life very difficult. It's not unright. It's not wrong. It's just okay. F prime of x is equal to 2x plus 7 times x minus 8 1/3 plus Okay, how'd I do? Good. Excellent. I would expect you to get to that point. Now the fun begins. Last chapter, and even the chapter before that, we would stop there. Okay, because I was just concerned that you could do the product rule. We're moving beyond that now because what I have to do is set this bad boy equal to 0. So some of you did things like you distributed the 2 to the x plus 7. That's not wrong. It's just not what we want to do, and you'll see why in a second. This is a sum. Yes? There's a big honking plus sign in the middle. That's bad. I want to turn this sum into a product. Why into a product? Because that would allow me to make use of your friend and mine, the 0 product rule. If A times B equals 0, then what do you know? A equals 0 and B equals 0. If I can write this as a product and not a sum, then I'm good to go.
What if I could find?
But who knows?
What if I could find a number that I can plug in on both sides, so that both sides would equal 0?
Does that seem like a very efficient system?
But it works here.
Well, sure, yeah, because I gave you a nice, easy. But what happens when the number is 217 over 33?
Cry.
Yeah, there you go. Okay. What does this term and that term have in common? X plus 7. Okay. I'm just going to leave that there for a second. And x minus 8. Okay. Then a big honking bracket for everything that's left behind. And we talked briefly about this, but I'll go over it again. You want to take the more negative exponent out in front. So if I look at the x plus 7s, I've got a 1 and I've got a 2. The one that's smaller or more negative is 1, so this is good to go. The x minus 8s, I have one raised to the 1/3. I have another one raised to the negative 2/3. Which one is more negative? It's a negative 2/3. Then I go back and I see what I left behind. Well, I left a 2. And the reason we take the more negative out is because what happens when I factor out x minus 8 to the negative 2/3 out of an x minus 8 to the 1/3? What does it leave behind?
Is x minus 8?
X minus 8. Plus, I took one of those x plus 7s out of there. I left one behind. This whole thing went away, and I've got a 1/3 in there. And all that equals 0. So now we can apply the 0 product rule 3 times. I've got 3 things that multiply together to give me 0. Each one of them has to equal 0. So I'm going to start a list down here. My critical numbers. X equals, what are they? Negative 7, 8, and then whatever mess we get out of this bad boy. So that would be 2x minus 16 plus 1/3 x plus 7/3 equals 0. 7/3 x. 16 is 40a, 7 is minus 41/3 equals 0. Come down here. 7/3 x equals 41/3. So I'll multiply by that. The 3's will cancel. I get x equal. If I did my math correctly, I have 41 over 7. Or did I screw up somewhere? So 2 is 7, right? Okay. So there's my other critical number. 1, 2, and 3. And again, that's why we put that off, because I didn't care if you could get that last chapter, because there was no reason to set it equal to 0 and solve. Now, it's a mandatory part of this problem to find out where those critical numbers are. So getting back to your point, Smarty Pants, you got the negative 7 and the 8. Would you have gotten that bad boy?
No.
No. I mean, you could be guessing until you're my age before you did that 41 sevens. Questions? This process you're going to do over and over again. The problem is, or one of the many problems, is there's a lot of spots to make mistakes. And most of the problems that come up here happen for something simple, like a sign error. Or adding -16 and 7/3 incorrectly. Use your calculator. If you're not good with fractions, you can easily type in -16 plus 7/3 in your calculator and get your answer there. Good? Oh, I gotta erase this. Hold on. We're going to skip this one because it's another example. But there's a function. And we could do a calculation. This is a real world example. I got this from some nerdy physics book. That they have the velocity of the Hubble Space Telescope when it took off. And that was the actual velocity of the function. And you can calculate where the Hubble Space Telescope was traveling its fastest, where it was the slowest, by finding the max and mins of that problem. Okay, we're not going to do it. It's a waste of time, but I just wanted to show you that it does have a practical application. And you recall, of course, that the velocity, the derivative of the velocity is acceleration, so we could also talk about the acceleration of that bad. Okay, so that's part one.
What does that mean?
Well, that's what I'm asking you. Do you get it? What is this? I should say, what are these? I'm sorry? These are relatives. What's this? What kind of Nissan? No. No.
Damn.
It's a Nissan Maxima. And I don't know why that just happened.
They wanted to wrap it up.
Yeah. I think I just broke it. Okay, give me a second.